Hello, today I'm going to be making a quick video on floating point representation in binary because we went over this in lab and I saw some confused faces as well as office hours, so I think this might just be a good resource to have to sort of look back on when you're studying. So yeah, let's go ahead and get right into it. So what is the problem that we have? So right now, throughout the first week or so of this course, we talked about unsigned integers, and then we said, okay, what if we wanted a negative number? And we were able to do that thanks to, well, first thanks to signed magnitude, but that one kind of sucks. So mainly thanks to two's complement. So two's complement, awesome. But now brings us to the next point, which is what if we wanted to represent a floating point? So a number that has a decimal in them. So that could be like 10.1, 7.3214, whatever, anything like that that has a decimal. So the way we might do that with binary is binary point. So looking at this, it's kind of over here on the right, the same sort of setup that we've had before, where we got the sums of powers of 2. So this one, still 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, and so on, and so forth. Same thing going the other way to the right of the binary point. And we call this a binary point. It's like a decimal point, but because we're in base 2, we're going to call it a binary point. So if I slip up and call it a decimal, just know I really mean the binary point. Okay, and so to the right of that, we got 2 to the negative 1, which we know is going to be 1 over 2, 2 to the negative 2, 1 over 4, 2 to the negative 3, 1 over 8, and so on and so forth as you keep getting further to the right of that binary point. So if we were going from binary, given a number like this, and we wanted to get it into decimal, it's pretty straightforward. And it's kind of like what we've been doing beforehand. So this number here on the right, we would have 2, right, this one, plus 2 to the negative 1, plus 2 to the negative 2, which we know is 2 plus 1/2 plus 1/4. And that is going to give us 2.75. Nice. Okay. Slightly harder than that is going to be, we're given a decimal number, so something like 10.75. And we want to get it into this binary. Now, this is slightly more tricky. The first thing we want to do when we see something like this is look at the integer part. So in this case, that's everything to the left of that decimal. I'm saying decimal because we're in base 10 here. And so 10 in binary, 1, 0, 1, 0, because that is 2 plus 8, 10. Okay, cool. We will add our binary point, and then we are going to look at the fractional remainder that we have. And in this case, it's 0.75. Now, if I want to, I can just look at that really hard and say, well, okay, I know 0.75. I can break that up into 0.500 plus 0.250, okay? And then I can simplify that even more. I'll say that's 1/2 plus 1/4. And oh my God, look what's happening. That's 2 to the negative 1 plus 2 to the negative 2. That's a sum of negative powers of 2 like we have over here. Okay, so we can just add this up and we'll say it's a 1 and a 1 right there. And that is our number, 10.75 with the binary point. Okay, so this brings us to kind of an issue is, oh my God, what if the fraction was janky? What if it was not a very clean, 0.75 like that we could do the sum of fractions of 2 in our head? Okay, and so the way that we are going to solve this is with repeated division. And this, we're going to call it a slightly medium hard problem. And the steps are over here on the left. So after you get the integer portion, which is like what we did earlier with the 10 going into 1010, we are going to take the fractional remainder. We're going to multiply it by 2. If that result is greater than or equal to 1, we're going to append a 1 to the right of the current binary number. We're then going to subtract 1 and repeat. If that result was less than 1, however, we're going to append a 0 to the right of the number. And then we're going to keep repeating until we get 0 as our remainder. So looking over here to the right, we're starting with a number, negative 12.6875, and we're trying to get it into that binary point representation. So first thing is we're going to look at the integer part. So we're going to say negative 12 in decimal is, well, it's pretty easy. We'll say negative, oops, that's not very good, negative, and then we are going to do 1100, because that's what this is 1, 2, so 4 plus 8, that's negative 12. Cool. Then we're going to put our binary point right there. And now it comes sort of the tricky part, which is the repeated division. So I like to make a little column setup like this. I'll use, say, maroon to start. And we're going to get this fractional remainder. So 6, 8, 7, 5. First step says multiply by 2. Okay. Times 2. And that is going to give us 1.375. I'm using a calculator because I will not be doing that by hand. And we're looking at our result. Is it greater than or equal to 1? Yes, it is. So we are going to append a 1 up there to the right of our binary number. Next thing we want to do is subtract. I'll use blue here. Subtract 1, bring this down, and we're going to repeat. I'll do me. Okay, so 0.375 times 2 is going to give us 0.750. Is that greater than or equal to 1? No, it is not. So we are going to put a 0 right there. Then we are going to bring this guy down, 0.750, multiply by 2. That gives us 1.5. Is that greater than or equal to 1? Yes, it is. We're going to append a 1, subtract 1, bring him down, multiply by 2, 1.000. Is that greater than or equal to 1? Yes, it is. We're going to append a 1. And then, if you realize right here, that's a terrible blue, we can use this. Bring down the 0.000. Doesn't matter how many times we multiply by 2, 0 is never going to change, okay? So at this point, we are good to stop. All right, and we have our binary point representation right here. So it's a negative 1100.1011. But this kind of brings us to the next problem, which is, how is the computer going to store something like that? Okay, what if these were really long? We only have 32 bits we can use to store it. And does the computer know what that is? How are we going to tell the computer where do we put that? What if the binary point was here, for example? What about the negative? How are we going to tell it that? If we're using all of the digits that we have to represent the number itself, we're not going to be able to put in key information like that. So that brings us to the next point, which is the solution, and the point we were trying to get to is the IEEE-754 format. And this is going to be the standard for representing floating points via 1-bit sign, represented by an S, an 8-bit encoded exponent, represented by EE, and then a 23-bit mantissa. And so the formula that we're going to use is we know our number is going to equal -1 raised to the sign times 1 point mantissa. So this is an understood 1 point. We're going to assume that that 1 is always there, and then we're only going to use the mantissa in our representation, times 2 raised to the encoded exponent minus 127. So what are the steps to getting this IEEE format once we have our binary point representation? The steps are going to be, we're going to look at it. We're going to say, okay, is this positive or negative? Then we're going to get it into scientific notation. Then we're going to get the mantissa, and then we're going to do the encoded exponent. So looking at this one, I think sure pink would be a good color. We know that this number is negative. So our sign, the first bit in our answer, is going to be a 1. Okay, 1 for negative, 0 for positive. Step 2 says we need to get the binary point into scientific notation. So if you've had to take like chemistry or physics, unfortunately, they know that they always do numbers like this, like 3.754 times 10 to the 3 or something is really just equal to 3754.0, because like there, it's the number of times you move that decimal point over. So we want to do that, but just in binary. So I will do red for this one, and we know that we have -1100.1011. We want to get that into scientific. I'll say to scientific, and that is going to be 1, 2, 3. So -1.1001011. And so that kind of looks like what we have in the actual formula, okay? So that's the format we got. 1 point mantissa. So we know that this is going to be our mantissa. So we will say mantissa is equal to 1001011. So now we almost have everything we need in our formula, right? We have the sign, we have the mantissa. The last thing we got to do is this encoded exponent. So looking at this number right here, what would we need to do to get it back to our actual number, the value itself? Well, we would need to move this binary point over by 1, 2, 3. And we know that shifting binary point is going to be the same thing as like multiplying it by 2. So we multiply by 2 3 times. We know that we need to do 2 to the 3, and that needs to be equal to 2 to the encoded exponent minus 127. So then we can just set this up. This is a pretty easy addition problem. So 130 is equal to our encoded exponent. All right, and there's a good lab slide that we talk about with why we actually do this minus 127 with the biasing, and it has to do with we want all of the exponents to be like unsigned values. So we don't want to have a negative number so that we can quickly compare bits and see which value, if we have like two values that are stored as floating points, which one is greater. Yeah, so now we have 130. We know that we're going to have to represent that in 8 bits. So 130 in 8 bits is 1, 0, 0, 0, 0, 0, 1, 0. All right, and that's our encoded exponent. And so there you go. We have sign, we have the mantissa, and we have the encoded exponent. Last thing to do is we just put them all together for a final answer. And so sign comes first, followed by the mantissa, or followed by the encoded exponent, excuse me. 1, 0, 0, 0, 0, 0, 1, 0. And then we have our mantissa, which is going to be 23 bits. I would really rather not write all of that out. So I'm going to do this, 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 and then we'll say the rest of these will be zeros. All right. So that is how we would get a string of 32 bits to represent that number that we started with, which was negative 12.6875. So I hope this video was helpful. Thank you very much for watching. If you have any questions, feel free to either comment here or comment on Piazza, come to office hours. Yeah.